Okay, I'm going to show you a quick way to compute the area element in polar coordinates. Namely, how do you show or remember, really, that the area element can be written as r dr d theta, or more suggestively as r d theta times dr, where this is the theta contribution, this is the r contribution. So you can memorize this, but this does not really translate well to spherical coordinates, which is this will show up later, but way that'll work in both cases. And also the book's explanation, which uses the area of a sector, this polar rectangle, they call it a sector. It requires knowing that this can be written like 1/2 r squared delta theta. You need to know that you need to know this calculation, and this also does not generalize to spherical coordinates. Like I can tell you, when I use spherical coordinates in practice, I do not remember it by the area of some spherical sector, because that just so. Again, I want to try to give you something that a quick trick that will work in both cases. Let me just motivate why this works really quickly by showing why the trick works in the Cartesian coordinates. So what we're going to do is we're going to write this as an x change, an x increment times a y increment. So I'll write it like this: delta x r, the length of the r increment, times the length of the y increment. And what is this y increment? If we have our position vector r xy, what I'm going to do is I will shift x dx. That's a little larger than what y, and dy, x, y plus dy. And now let's take the area of this square. The area is simply dx dy. And we know that because it is the length of the sides. So the length of the x side times the length of the y side. And this is delta x r. This is delta y r. And of course, these are sides, right? So really what I'm saying is that delta x r is r when you increment by the dx, and then minus r. And really what this is just to illustrate what's going on. The Taylor expansion of f of x plus dx minus f of x is, of course, dx plus small terms. So if dx is really small, this is just the partial derivative of r times dx plus something small. So what I've shown is that dA is the partial derivative of r times dx times the partial derivative of r times dy. Okay, the point of why did we that if you replace x with r, and you replace y with theta, then it still works. And the reason is it's still a rectangle. So that is to say that area, it still corresponds to a rectangle. There's a right angle between these increments. And that reason is that if we just look at the position vector, we increase the radius, it goes in the radial direction. And now if we increase the angle, then at least near the origin, this is in a perpendicular direction. So we have our right angle, so we can make a good square, or rather rectangle. So the upshot is that in polar, you can make a rectangle with increments. So let's just look at what this looks like. So now we increment in R. So now we have R of R plus delta R comma theta, treating R as a function of R and theta. Remember, if we use X and Y, what it is in polar coordinates, this is R cosine theta, this is R sine theta. So when I'm saying R plus delta R, I really just mean increase R slightly. So now we increment in theta. So now we have R of R plus, no, I'm sorry, R. And what we do now is we form our favorite rectangle. And now we form its area. So dA will be the length of the sides. So I'll just say here, the length of the R side times the length of the theta side. Okay, now the length of the R side is as before. Well, we can just do it. I think it just adds an extra line. So R of R plus delta R minus R times R when you increase theta slightly minus the original R. And by the Taylor expansion, this is the partial derivative of R with respect to the radius times dr. And then we have a similar term with the theta. Okay, so let's just factor out the d's. So we have the radial change times the angular change times dr d theta. Okay, so all we need to do is just compute these things, but this is actually really easy, right? So just take the partial derivative, we get sine. So now if we take the length, well, this lives on the unit circle. So that's 1. So this first term here is 1. So now let's do the same thing with the theta, and we'll get something slightly different. That weird extra r. So if we take the partial derivative of theta, then we get minus r sine theta, r cosine theta. Maybe we can factor that r out. So now let's take the length of this. And then we finally get r. The r factors out of the length. And then this again lives on the unit circle. Sine squared plus cosine squared is 1. So it's just r times 1. So that means the second term here is r. And so we conclude that dA is r dr d theta, and that's exactly what we wanted. So the same trick works for spherical coordinates, which you don't know right now, but you'll see. And it's a much quicker way than or maybe not as quick, but I think it's much less to and more systematic. Spherical sector or the Jacobian. Okay, thanks.